Okay, part 2 of 15.4, we're going to look at weak acid titrations. So similar process, except once we do the neutralization, we have to analyze a little bit more carefully what our products are at the end. So titration, here we've got formic acid, 0.2 molar, 50 milliliters is titrated with sodium hydroxide. Classify this, we have a weak acid titrated with a strong base. Calculate the pH. Part A says at 0 milliliters of base added. At 0 milliliters of base, we only have formic acid. And the volume doesn't matter because there is no volume change. So that 50 milliliters doesn't really matter for part A. So we just want to handle this like a formic acid problem, okay? So part A, we have a weak acid only. What do we do with a weak acid? Well, it's an equilibrium. HCOOH dissociates into H plus HCOO minus. We set up our equilibrium here. We have a 0.2 molar formic acid. We always do our ice charts in molarities. And then we have no hydrogen or formate yet, minus X, 0.2 minus X, plus X, plus X. So we're just looking at our problem here, and we get x squared over 0.2 minus x equals our Ka, which is 1.8 times 10 to the negative fourth. So before the titration has even started, we have a concentration of hydrogen of 0.00591 molarity. That is my x value, which is also hydrogen. The negative log of that is the pH, 2.23. And I gotta fix that, 2.23. Okay. So the pH at 0 milliliters of base, the initial is a weak acid problem. Part B. Part B, now we have 5 milliliters of sodium hydroxide. So we have some volume changes, and since I'm adding a base, it's going to react with my acid. So to start with this one, I do not have an equilibrium problem. We have a neutralization problem, and this is a limiting reactant. So we have our formic acid, and it's going to react with the hydroxide. We don't care about the sodium, it's a spectator, although we could dilute that and figure out its new molarity with 55 milliliters of solution. And then we're making water, and the formate, HCOO minus. Okay, so this is different. This is an acid-base reaction, limiting reactant, neutralization, and this is all going to be in moles because we have volume changes. So now we look at the 50 milliliters of the acid, 0.2 molar of the acid. We have how many moles is 0.01 moles. 5 milliliters of my base at 0.4 molar gives me 0.002 moles. So that is my problem. We don't have any of the formate out to start with. Limiting reactant here, we can see that just at the beginning, the hydroxide is going away to 0. So we're going to lose 0.002 from this formic acid and be left with 0.008 moles. And we're going to make some of the formate, 0.002 moles. Now the volume's changed, so we have 55 milliliters, 0.055 liters. And we're going to get molarities of these. The formic acid is 0.145 molar, and my formate ion is 0.0364 molar. Now this is a conjugate pair at the end. I have my formic acid left and my conjugate formate. This is a buffer problem now. We have to analyze what are we left with at the end. My conjugate pair gives me a buffer. So how do we calculate the pH of our buffer? Well, what we would like to do is going to do our Henderson-Hasselbalch equation. That's probably the easiest. We could do the Ka of the formic acid and just start out with some of our base to start with, and then the hydrogen is the only unknown. But Henderson-Hasselbalch is just as easy when you recognize you have a conjugate pair. So my pKa for this, negative log of the Ka, 3.74, plus log of the base over the acid, products over reactants, 0.0364 molar over 0.145 molar. That's going to give me a pH here of 3.14. So we added some sodium hydroxide, but the pH didn't change too much. If we continue on here, we'll stay on the same page. Our part C asks us, what is the pH at the midpoint? They don't give us a volume. Remember at the midpoint, if we look at our same equation, HCOOH plus the hydroxide is going to equal H2O and HCOO minus. At the midpoint, when half of this has been neutralized, this is my hydroxide is still my limiting reactant, then if I'm going to gain that amount over here for the conjugate. So when those are equal, that is our point where our pH equals our pKa, because the log of 1 is essentially 0, so the pH equals the pKa. So at the midpoint of a weak acid-base titration, the pH is always going to come out to our pKa, 3.74. All right, that's the nice part about Henderson-Hasselbalch. And at that point, we say that the formic acid and the conjugate ion molarities are equal, so the pH equals the pKa. When we get to part D, it's a little bit trickier here because they just tell us with words that we're at the equivalence point. Now that's okay for the midpoint because we just say the pH is the pKa. But at the equivalence point, there is a volume change and we don't quite know what it is. But those words, equivalence point, should at least conjure some numbers in our head. So let's figure out what we're working with. We still have the formic acid, and we're adding hydroxide to it. And we're going to generate, that's a single-headed arrow. We're going to generate the water and the formate ion again, acid plus a base. Acids give hydrogens, bases take them. This is still going to be a neutralization reaction. There is a volume change, so we're in moles. Now our formic acid that we were working with before, we've got 0.01 molar. I'm sorry, that's 0.01 moles, not molar, 0.01 moles of the formic acid. And when we say equivalence point here, we know that we also have 0.01 moles of base because the acid and base are equal at the equivalence point. So at the equivalence point, we know that this is totally neutralized. We don't have any formic acid left. We don't have any hydroxide left. That means the only thing we have over here is our product. And we don't have this in a strong acid-base titration, but in a weak one, we have 0.01 moles of my formate ion. All right. Now we need to get that into a molarity, which means we need to worry about volumes. For the volume of the base, it's not given. But we do know that when we say equivalence point that these numbers are equal. So we've got 0.01 moles of the base. And we know that we have 0.4 molar solutions, so 0.4 moles per liter. So the volume of the base there is going to be 25 milliliters, 0.025 liters. So 25 milliliters of base, and we had 50 milliliters of acid. That's going to give us 75 milliliters total. So the formate ion is going to be 0.133 molar. So again, just to recap here, we neutralized our formic acid with equal amounts of hydroxide. but we had to calculate the volume change of the sodium hydroxide to know how to dilute my product at the very end. Now at the very end we're left with the formate ion. This is a weak base all by itself. There's nothing else in there, so we have a weak base. So how do we calculate the pH of a weak base? Well, we just solve a weak base problem with a Kb. So we get a new reaction, and we have our HCOO minus plus water. Bases take hydrogens, so now we're going to make the HCOOH plus the hydroxide, which is really the reverse of the top one. Equilibrium says, hey, these 100% these react, but it's not going to stay that way. Some of it's going to kind of react backwards with sig figs and depending on Kb. This is how we kind of think about our weak base problem down here. This is an equilibrium, and we say we've got 0.133 molar solution. None of those to start with because they were both gone before. Minus x, 0.133 minus x, plus x, plus x. And let's make some room. Our x squared is going to be 0.133 minus x equals our Kb. Kb we have to solve for, which is Kw divided by Ka. So we're given a Ka in this problem. Kb then is 5.55 times 10 to the negative 11th. So we have to solve for that. We can't just use it. Our x value here is going to come out to be the hydroxide, 2.72 times 10 to the negative 6th. Negative log of that gives me a pOH, because it's hydroxide, of 5.57 and a pH of 8.43. And we need to make sure that makes sense. We have a weak base at the equivalence point. My acid is gone. We have a conjugate base only. So if this is a base, our pH is above 7. And at the equivalence point, we should see our pH above 7. And we do. And here's how you see that on a graph. We have a weak acid with a strong base. We want to recognize that we start with a low pH, and this little hump here is different than the strong ones. That's because we're making our buffer, and then in here the buffer keeps the pH from changing too much until we get to our equivalence point, where at the beginning we had our strong acid only, or weak acid only, sorry. Our equivalence point, we have the conjugate base only, and the pH is greater than 7. So that's your clue that your titration curve is a weak acid titration. If we had a weak base problem, then our equivalence point is going to be flipped upside down. So at the beginning, we have only our weak base. Let me do ammonia for an example. And then it gets titrated all along the way here, midpoint, and we're slowly generating the conjugate. So our conjugate acid is all that's left at the end. In this case, it would be NH4+, which is a weak acid problem. So if we have an acid at the equivalence point, our pH should be lower than 7. The only pH that's at 7 is a strong acid-base problem. So conceptually, we want to be able to differentiate a strong and weak acid-base titration curves and how they are different, and then kind of what is being generated, this limiting reactant problem all along the curve here. Okay, last problem. We've got 3 parts to it. It's another one. Calculate the pH of each of the following points. Now we're going to titrate a weak base with a strong acid. So 50 milliliters of a 0.01 molar sodium phenolate, and the sodium there is going to be a spectator, and the phenolate is a negative ion that can accept hydrogens with a 1 molar hydrochloric acid, and the chlorine is going to be a spectator with that one also. So initially, let's treat this the same way as we did before. Initially, we have the phenolate, which is a weak base. So we have a weak base problem all by itself. The volumes don't matter yet. No volumes have changed. We don't need the acid. So the OC6H5 minus plus water is going to make HOC6H5 plus hydroxide. So a weak base problem, this is an equilibrium. We need a Kb, 0.01 molar, because we want everything in molarities for equilibrium problems. We don't care about the water. 0, 0, minus X, plus X on the product side. Okay, so we get X squared over 0.01 minus X equals Kb. Now we need to solve for a Kb for this problem because we're just given a Ka. So our Kb, because this is a base, so keep all the base terms together, is going to be 9.25 times 10 to the negative fifth. Okay, we plug that in, we get an X value of 9.29 times 10 to the negative fourth. That's my hydroxide as well, which is what we're concerned with for the pH. So my pOH, negative log of that number, is going to be 3.03, which 14 minus that will give me a pH of 10.97. So we just got to keep our acids and bases separate. pOHs, Kbs, hydroxides, keep that separate from pH, Kas, and hydrogens. Part B is another kind of simplistic one here. Calculate the pH of a midpoint. Well, at the midpoint, the HOC6H5 concentration is going to be equal to the OC6H5 concentration minus, which means the pH is going to equal the pKa. Now we got to be careful here. We want the Ka for this one, not the Kb. pH measures pKa. pOHs would be correlated with pKbs, but that's not what we measure. We want pHs. So to get our pKa, we just take the negative log of the Ka, 1.05 times 10 to the negative 10th, and our pKa then is 9.98. That's our pH. And that's above 7, because the phenolate is a little bit more, is stronger than the acid conjugate. So 10 to the negative fifth versus 10 to the negative 10th. So that will take care of itself. We do the pKa, and we see that that midpoint is indeed above 7. Part C of that same problem, it's kind of reset, is the equivalence point, which is the same as before. We know in words what that means. Mathematically, that should generate some numbers in our head, but we need to calculate some volume changes. So, neutralization problem. We have our phenolate, OC6H5 minus, plus the acid is going to make HOC6H5. And we need everything in moles here to calculate our volume changes. So now if we look at the number of moles, we've got 50 milliliters of a 0.01 molar solution. This is a pretty small number of the phenolate, 0.0005 moles. The hydrogen, 0.005 moles. Also, 0.005 moles, sorry. Because equivalence point, those have to be equal. So we get to our phenolate. Both of those are going to go to 0, so minus 0.0005. Equivalence point, those are both gone. We're going to add that over here, 0.0005. 5 moles. So we get 0.0005 moles. And to get the volume of the acid, we need, again, to consider the equivalence point, we needed 0.0005 moles of acid. It's a 1 molar solution, so 1 mole per liter. So we need 0.0005 liters, which is half of a milliliter to get to the equivalence point. Not much at all, but those molarities are very, very different. So we add that half a milliliter to our 50 milliliters of the phenolate, and we get 50.5 milliliters, so 0.0505 liters. And our molarity here is 0.0099 of our acid. Okay, so we don't have anything left on our reactant side, and at the end of the problem we have a product that is a weak acid all by itself. So to solve for the pH, we need to do a weak acid problem with our new molarity. So we have our weak acid, HOC6H5, dissociating into H plus and OC6H5 minus, 0.0099. None of those because they ran out. This is an equilibrium problem. So let's get our ice chart in there. Plus X, 0.0099 minus X, X and X. We plug this in and we get X squared over 0.0099 minus X equals our Ka. And Ka is given in the problem, 1.05 times 10 to the negative 10th. Our X value here is going to come out to 1.02 times 10 to the negative 6th. And that is my hydrogen because this is an acid Ka problem. So my pH, negative log of that, is going to be 5.99. And that's how we want to handle a weak acid and weak base titrations. Careful analysis, there's always going to be these two steps with weak acids and bases. We go through our neutralization. There are volume changes. Sometimes you have to calculate the volumes, but then once you're done, you have to analyze what you're left with on the product side. Do you have a buffer if you have the conjugate pair? Do you only have the conjugate that you made? Sometimes you have excess of the strong acid or base that's added, and then you need to solve that problem appropriately in a second step. And that should wrap up 15.4 to look at titrations.